I am going to discuss the combining residual networks with LSTMs for Lipreading research paper. The central idea of the paper is to design an end-to-end deep learning system that can recognize spoken words using only visual information from lip movements in video. The authors achieved this by combining three neural network components in one architecture, and this combination allows the model to recognize words purely from lip movements. There are three main works that the authors draw from. The input data is the lip reading in the wild dataset. The LRW dataset contains video clips of people speaking words collected from BBC television broadcast, and this dataset is challenging because it contains significant variability and simulates real-world conditions. The implementation process is shown in the block diagram. The first step in the implementation process is pre-processing. There are 4 steps in pre-processing: face detection, mouth region extraction, frame normalization, and resizing of frames. Only the mouth region of interest is used so that the network focuses on lip movements rather than the full face. The second step is the spatiotemporal convolution layer. This layer performs 3D convolution across both space and time and learns short-term lip motion patterns. After convolution is done, max pooling is applied. The third step is the residual network. The authors use a 34-layer residual network which uses skip connections. This allows training of very deep networks. This stage produces high-level mouth features. After the ResNet layer's global average pooling is applied, which reduces each frame's feature map to a feature vector. Fourth step is bidirectional LSTM layers. Because the LSTM layer is bidirectional, the model processes both the forward and the backward time sequence. This layer captures temporal dynamics of lip motions, and the sequence corresponds to a particular spoken word. This is then passed to a fully connected layer where the output corresponds to the vocabulary size. The final layer applies the softmax function to convert outputs into probabilities. The predicted word is the highest probability class. The authors performed several experiments to evaluate the proposed model. The baseline model is a multi-tower VGGM which has a top-1 accuracy of 61.1%. The first model contains 2D CNN with ResNet and temporal convolution, which is an improvement over baseline by 8.5%. The second model uses 3D CNN instead of 2D CNN. It improves over N1 by 5%. The third model replaces the ResNet with the deep neural network. ResNet improves accuracy by 4.9%. The authors replaced temporal convolution with bidirectional LSTM. A single bi-LSTM layer provides improvement of 3.8%. Two bi-LSTM layers provides improvement of 1.2% over a single layer. Finally, end-to-end training is done, which provides an improvement of 1.9%. The final model uses two-layer bi-LSTM and concatenation of forward and backward outputs. This gives performance gain of 21.9% versus baseline and 6.8% over the previous state of the art. Errors usually occur between visually similar words. These are words which share similar phonemes or clips that contain co-articulation from neighboring words. The best recognized words have distinct mouth movements, while the worst recognized words have less distinctive visual cues. That concludes the presentation. Thank you.